The following 16-bit binary adders A and B are added together using. So the thing is, they wanted to add these 16-bit numbers, right? So this is a 16-bit number, it has 16 bits, 1 to up to 16. This is also a 16-bit number, it has 16 bits, right? Now they wanted to add the two of them, right? But they didn't want to use the regular adders, right? They wanted to use another called the carry look ahead adder. I think you have seen the diagrams from it, right? Usually looks like this one, right? There's a carry look ahead unit, and there are separate smaller adders, right? Whose inputs are combined, right, to predict the next carry, something like that, right? So now what they did is they are trying to use they are trying to use 4-bit carry look ahead adders. What it means is that they will take a 4-bit carry look ahead adder, right, for only the first maybe these 4 bits. Take another 4-bit carry look ahead adder, take another 4-bit, and so that these ones, the output will feed into this, feed into this, feed into this, right? So this one, like they segmented the adders, right? So that's what the question is. And it says generate the signals gene 0, gene 1, gene 2, gene 3, right? And capital G 0. So this question A. And the carry propagate signals P0, P1, P2, P3, and capital P0, right? Now, the thing is, you are fortunate, right? The formulas for G0 and P0 are simple. G0 means just end the two inputs, right? Any G means end the two inputs, right? And any P means all the two inputs. So that's all, right? So for example, G0, right? It means that evaluate for what? This one, this first 2 bits. So when I end 1 and 1, what do I get? 1, right? So you realize that here's 1, right? When I end 1 and 1 again, for the second bit, 1. When I end 0 and 0, 0. End 0 and 1, 0. So you can continue. Then the next part is PI, right? The PI is also just all gates between the two, right? You see, the formula was generated from the other actually, so you can go and look at that and everything. But I mean, to solve this question, this is what you need, right? So P means just all the two. So you realize that the answers here are just all. So when you all this, the answer all, right? You can do that one. Now, when you finish, so that's the G0. So for example, here this one is G0. The first bit is G0. The second bit is G1, G2, G3, right? But in solving the question, they have just done G0 to I think G15. They've done all of them, so that in the next questions you will not worry yourself. But I mean, yes. So when he was saying G3 down to 0, so 0, 1, 1. He's just saying that from Gene 0, Gene 1, Gene 2, Gene 3 is just what 1, 1, 0, 0. So that's what it is. So don't worry about that one. But the next part is the capital G. You see, there are small genes and capital G's. There are small P's and capital P's. Now the capital G means this formula, this whole formula, right? And it's a simple way to memorize it. It's just like a series, right? So this is how I memorize it. When they tell you capital G 0, right? Remember that in your adder, you have split it into what? 4-bit adders. 4, 4, 4, 4, 4, right? So when they tell you gene 0, that means that the gene output of this one is what you are talking about. Now, what is the highest bit in this one? Bit 3, right? 0, 1, 2, 3, right? So that's it. So it means that bit 3 will stand alone, right? Then now you get a decreasing term, P3 gene 2 plus. Now the p's will just be multiplying. So P3, P2, Gene 1. So when you do it up to Gene 0, like small Gene 0, you stop, right? So that's how the series is. Do you get the series? Oh.
Gene 3, 0, P3.
Then, should I explain it again? This,
Formula, the formula.
this is just a formula, right? But what it means is that we get the capital G, like the capital G from the small genes and small p's. So this is how we get, and that's the formula. Right? The formula is just small gene 3. Because you see, when we talk about gene 0, we are talking about the first address gene. When we talk about gene 1, we are talking about the second address gene. When we talk about gene 2, we are talking about the third address gene. When we talk about gene 3, we're talking about the fourth address gene, the fourth carry look ahead address. The first carry look ahead address gene is G0, right? And that gene, it stands from, like, its base starts from what? 0 to 3, right? So this will be a series from what? 0 to 3, right? But the formula, you realize that this formula will repeat a lot. So if you're able to just capture one, it will be okay. So it will be gene 3 first plus P3 gene 2, right? So it's like you are decreasing in genes, right? You are decreasing in P, but the P's will just be multiplying. So the first one will just be alone. The second one will be P3 gene 2. The second one will be what? P3, P2, gene 1. And then the next one will go to gene 0. Because you end at gene 0, right? You stop there. Right, so P3, P2, P1, G0. Yeah, the P's are decreasing. Right, yes. And you always end at what? A higher P, like one more P than G. Because anytime there is P0, it means that there is also the carryout, which is wrong for me. Right, so that's what it is. Anytime you see P0 inside, right, it's associated with something like C, there will be C inside, right? So always it will end at P1, right, or P less than something. So just keep it in your head. Now, when you are done, now the rest is just substitution. What is gene 3? Gene 3 is from here. Yes, so substitution. Right. So this is just so gene 3 is what? This is 0, 1, 2, 3. So gene 3 is 0. What is P3? P3 is 0, 1, 2, 3. So this one. And gene 2. Gene 2 is what? 0, 1. So you are just substituting, right? To get one long equation. So that's it. Now that's for the capital G0, right? For the capital P0, it's also the same thing, except that the formula is different. So for the capital P0, you multiply all the P's. So if it is P0, remember that capital P0 is also for the very first adder, right? The capital ones, it means that the whole adder is considered as one, right? So, and that whole adder is considered as one, bit 0 to what? Bit 3, that's first adder, right? So from bit 0 to bit 3, so you just multiply what? The P's from bit 0 to bit 3, so P3, P2, P1, P0, and that's a P, capital P0. And now you just go and fetch your P's from here. I believe that one you can do it, right? Then you are done. Now the next question is generate the signal for gene 4, gene 5, gene 6, gene 7. Now I'll not do it because gene 4, gene 5, gene 6, 7 is here. This is gene 4, this is gene 5, gene 6, gene 7. This is P4, P5, P6. Now let's calculate the capital genes, the capital P's. Right. So the capital gene will be what? Capital gene 1. The first one, remember that we're starting from what? 0 to 3. Right. But this time we are not dealing with this adder. We'll be dealing with the bigger adder, which is what? 4 to 7. And the same formula. So from 7 we'll end at 4. And the same formula. Yeah, P5. Yes. Then you just substitute. Then the next one is P, capital P1. Capital P1 is yeah, all the P. But all the P's, right? But this P is for the capital P, right? And this P is for the second adder, right? So just when it tells you any P, just check it is for which adder, so that you know the best to multiply, right? It's not multiply. Not multiply. You say that. Okay. Then the next one is they will ask you for gene 2. So gene 1 was for what? From 4 to 7. So gene 2 will be from what? 8 to 11. And that's what you see, 8 to 11. So the same procedure, right? Now, I'll not do gene 3 because you can. The only hard part, right, is when, yeah, it's when they tell you to find C, right? Now, if you remember, in your formula for finding gene, right? Your formula for finding gene, let me see if I can get that formula for you. So for the C16, right? Remember the same formula from the how you find your carryout, right? Given your genes. But because this one is a carry look ahead adder, which is combining smaller carry look ahead adders, right? It's combining 4-bit, 4-bit, 4-bit CLA. You can also conceptualize the genes as the small genes in the carry look ahead formula, right? So in this case, right, this formula if you replace the capital G's and the small G's, if you replace the capital G's by their small G's and the capital P's by their small P's, you realize it's no different from, right? When you are doing C4, right? Because this is what? 4 carry look ahead address, right? So C15 will be like you are doing 4 carry look ahead address, but I'll be using the capital G's instead of the small G's. Now this C0, right? It is actually the carry out, right? From the very first carry look ahead adder, right? So this C0 is 0 because now you can just check, right? If you add these 4 bits, you will not get a carry, right? This is 0, remainder 1, 0, remainder 1, 1, 1. You will not get a carry, so C0 will be 0, right? So that's why here is 0, right? So that's why here is 0, right? So that's the only thing you should note. And once you know those now, you can find C16. Maybe next time we'll tell you to find C12, right? Instead of C15, we'll tell you to find C12. Remember, C12 will contain which genes? It will contain gene 0, gene 1, and gene 2. Yeah, C12 will contain gene 0, gene 1, and gene 2. The highest gene will be gene 2. You get it? So it means that your formula will just start from what? Gene 2 plus P2, gene 1. Yeah, then you reduce. Yeah, so it's just a matter of knowing that formula, right? Yeah, and I think that will do for you. So that's for this question. Any problem? Okay. So let's solve this one too. So this one it says, given a memory values and a one address machine with an accumulator, what values do the following instructions load with into the accumulator? So you have a one address machine, you have an accumulator, right? And this is what we are given. They say word 20 contains 40, word 30 contains 50, word 40 contains 50, and word 50 contains 70. You can actually draw this machine, right? So for 20, for 30, for 40, what? For 50. They say 20 contains 40, so here will be 40, right? This is word 20. Word 30 contains 50, so here will be 50. Then word 40 contains 60, so here will be 60. And word 50 contains 70, so here will be 70, right? So this is word 20, this is word 30, word 40, word 50. Now, they said, what values do the following instructions load into the accumulator, right? Now, the instruction is load immediate 20. Anytime you hear immediate, don't go and look at memory. The value provided is the answer. Sure. So the answer will be 20. So A is 20. Do you understand? Load immediate 20. Right? It's an immediate loading, right? So the address will be specified in the instruction. Hey, the data will be specified in the instruction, sorry, right? So since you said 20 means I should just use 20. So that's 20 will be in the accumulator. That's all. You get it. The second one is load direct 20. Here you have to take your time. Load direct 20. Go and check address 20. What does it contain? It contains 40. So your answer will be 40. Do you understand? Load direct 20. See, this is word 20. Yeah, it contains 40. That's what load direct does. Right. The next one is load indirect 20. Load indirect 20 means go and what? Look at address 20. What does it contain? 40. Now use that 40 to point at the next address. No. The like address 40. Yeah, load indirect. Yeah, so it means that the address. Yeah, that. Yeah. Let me explain. Load indirect 20. So come and look at the place for 20, right? The value you find there, right? It contains the address of the operand. You understand? Because it's indirect. You understand? So come and look at location. This is location 20. This is location 30. Location what? 40. And the last one is 50. Right? Now the question says load indirect 20. So come and look at location 20. Right? Because this loading direct and load direct, they provide the addresses. It's only immediately provides the value. The rest usually provide the addresses, right? So the address is what? 20, right? So the address 20, what does it contain? 40. But because it's indirect, I can't pick the 40 as my answer. I have to go and use the 40 to find address 40, what address 40 contains, and that's my answer. That is why it's called indirect. I have to do it twice. It's not direct. I don't get it one time. Which one?
Address 40 no contain.
So address 40 contains 60, and that's what you see. So address 40 is not 60. Right? So the answer is 60. Then the next one is load immediate 30. I mean, the answer is 30. We don't have to watch. Right? The next one is load direct 30. So load direct 30, I have to go and check at 30. What does it contain? 50. So I'm going to do 30. I mean, immediate. Load immediate 20, I put 20 there. So load immediate. Then load indirect 30. Right? I have to go to address 30. Right? It contains 50. So I have to go and check address 50. So the answer is 70.
Load indirect number.
Yeah, the F load indirect 30.
Address.
So you have to go and check load indirect 30. The memory value at address 30 is okay. Okay.
Load immediate.
So the next one is you have an address field. It contains an instruction. An address field of an instruction contains the decimal value 40. So it means that you have an instruction, right? But the address field, like how do I say it? The instructions operand or address field is containing the value 40. When you're asking where is the corresponding operand located, right? Now, when they ask you where is the corresponding operand value located, now they say A, immediate addressing. Immediate addressing to be in the address field of the instruction, right? So if the address field contain 20, then the value operand will be 20, right? But this one was asking where. It didn't ask you what is the operand. It was asking where. So the operand will be in what? The address field. And the next one is direct addressing. Direct addressing then to be found what at memory location what 14, right? Because in direct we're going the data there is the operand there is actually what the one we specify in the address which is the address of the operand, right? So we have to follow it to get the what operand. The next one is indirect addressing. Then to be saying memory location with address in memory location with address in memory location 14. So this is a bit confusing. But let's first we need the memory location, right? Of the address in memory with location 14. So we'll go to location 14, right? And we'll use that memory location, right, to go and find the operand. And the next one is register address, and it means that we are specifying register 14, but we'll just say the register name. Then register indirect address, so memory location with address in register with 14. Yeah, this one you are just defining. Right. I think you guys can do this one. The start thing, or we should do it. Yeah. So I think this one too you can do it. Or let's do it. So using non-restoring division algorithm and the hardware below, perform division of the 4-bit numeral 7 by 4. It's 7 by 4 bits numeral 3. So you are dividing 7 by 3 actually in tabular form where the quotient and the remainder are located. Now, when you see a question like this, don't rush into go and draw your table. Check. Right. Here, you realize that the divisor is n bits. Sometimes, unfortunately, the divisor will be 2 n bits. Right. So it means I have to pad it to look like that. Right. So if your divisor out here was 2 n bits, it means I have to pad it so that 7 will look like 8 bits. So it will have 0, 0, 0 before the last 3 ones. So check, right? Then the next one is the remainder. The remainder is supposed to what? Have 2 n bits, right? And realize that this machine allows shift left, shift right, and also a right operation, right? And you're using non-restoring division. So this will inform how you should draw your table because there are many variations of the division algorithm, right? There are some of them where you have to make both of them 2 n bits long. There are some of them one has to be n bit, the other has to be 2 n bit, and so you have to. So this is what you get, right? Now you draw your table, right? Now the divisor. Remember the divisor here is n bit, right? And divisor is 3, right? So 3 is what? 1, 1. But because it's n bits, and the bit is defined as 4 here, so you have to make it 4 bits by adding zeros in front. We are doing positive 3, right? So 0, 1, 1. The remainder is what? 7, right? But 7 is also 3 bits, right? But because 7 has to be represented in 2n bits, see, this is restoring division. The initialization step, you have to set your remainder towards the dividend or yeah, the dividend, right? Because I think the 7 is the dividend, the 3 is the divisor. So you have to set the remainder to the dividend. Like that's the initialization. So this is the initialization. So you realize this is 7, but it has been made into what 8 bits. So initialization. Then now we start the division already. The first thing you do is that you subtract. I hope you can do subtraction, right? Now one yeah, yeah. So this one, instead of doing long subtraction, they are just finding the tooth complement of 3 and they are adding it to 7. And now be careful. You add it to what? The first 4 bits. See, this is 4 bits. You add it to the higher order bits, right? Of the remainder. So when you add it to the higher order bits of the remainder, you realize that hey, you get a negative number. Now, if it was restoring division, you try to retrace your step, right? Before you shift. But this one, you don't retrace your step, right? You use the same number. When you come to
this one, did they shift first?
this one here, you have to shift first. Like at the beginning of every step, right? The first thing you do is you shift,
Sure.
right? At the beginning, the first thing you do is you shift, right? So you shift left once, right? Before you subtract, right? That's the algorithm for non-restoring division. Now, this is the answer we get for stage 1. We are going to use it to start stage 2. We will not restore. So we come back, shift left once, right? Now, when we shift left once, you realize that we have a negative answer. So this time, instead of subtracting, we'll add, right? And that's what they are doing. So they are adding 3. And you add 3 to the higher order bit. Now after adding, we still have a negative answer. But we'll not restore because this was non-restoring. So we shift. Now we shift, we still have a negative answer, we add. Now we have a positive answer, right? Immediately you get a positive answer after adding or even subtracting, right? It doesn't mean it means that you have to set yeah. So immediately after subtraction, after addition or subtraction of your this one, your divisor, you get a positive answer. Now you know you get a positive answer if your first bit is 0. You get a positive answer. The requirement is set the last bit to 1. Right? You see, they skip that step, right? But they just tell you to set the last bit to 1, right? Then now you go again, you shift left, right? Now because you have a positive answer, you continue about subtracting, right? And when you subtract, what did you get? You get a what? Negative answer, right? But because you've ended the number of steps, you see, this is 4 bits, so it means that at the end of 5 steps, right, you should have end. So 5 steps is what? 1, 2, 3, 4, 5. At the end of 5 steps, you should be done. You should produce an answer, right? So now after subtracting, we get a negative answer. It is only at this point that if you get a negative answer, you have to restore, right? And that is so that's the restore process. So after restoring, then we get this as our final answer. You understand? Restore means it was negative, so just transform it to positive, right? So you realize that here and here are the same because we subtracted 3, we added 3, and it's the same thing. Now what you get is your answer, but this is not your how you present your answer. You just tell them that what your answer is contained, the quotient of your answer is contained in the first 4 bits. So it means that this side is yours, the first 4 bits. See what I'm shading. So the quotient of your answer is contained in the first 4 bits, right? So this one, this is your quotient, right? And your remainder is contained in the what? Upper 4 bits. So this is your remainder. You get it. So you can even check from here if you are correct. What is this quotient? This is 2, right? 0, 0, 1, 0 is 2, right? And 0, 0, 0, 0, 0, 1 is what? 1, right? So what you are essentially saying is that 7 divided by 3 is what? 2 remainder 1, right? So you are done. So that's the process. I think this one you guys will go to do or should go through. The think they gave you the diagram and they ask you to perform this instruction, right? No, there are a lot of things actually, right? So they ask you to perform this instruction. The instruction is to move into R2, comma, the address specified by what R1. Now, usually, they will give you a whole bus, right? So I think we should look at the bus. In fact, there is a video on this actually, so you can use that one.
Yes,
Yeah, the same question, but